Let us start with the equation derivation.
Hmm.
Nernst equation derivation. That is what we will be discussing. Nernst equation derivation. So first we will understand what is this Nernst equation is. What is the importance of this equation?
Hmm.
Then we will derive this.
Hmm.
So the first point of discussion is the Nernst equation itself.
Hmm.
Nernst equation.
Hmm.
So what is the significance of this equation? Basically, this Nernst equation is used to calculate the electrode potential.
Hmm.
Used to calculate the electrode potential of an electrochemical cell. Now, what is this electrochemical cell?
Hmm.
Electrochemical cell is a special type of cell which can convert the chemical energy into the electrical energy.
Hmm.
So this electrochemical cell, it contains cathode and anode. Two electrodes it contains, we call it cathode and anode. So oxidation and reduction is taking place, and naturally a chemical reaction is taking place.
Hmm.
And because of that, ions are flowing in water, and water ions are charged particles, and flow of charge gives the electricity, and
Hmm.
we are able to generate electricity from that chemical reaction.
Hmm.
And this is has tremendous applications, electrochemical cells. Like we use inverter batteries.
Hmm.
So the batteries which we use, they also work in the similar phenomena.
Hmm.
Like we charge the battery, and then we can generate electricity from that battery.
Hmm.
Like in the car also we have battery, or in the home like inverter we use battery with that, like big batteries.
Hmm.
So electrochemical cell. So now we got an idea that in an electrochemical cell, what is the phenomena? The main phenomena in the electrochemical cell, conversion of conversion of chemical energy, conversion of chemical energy into the electrical energy. For example, I have a cell like this. Like I have a container.
Hmm.
Yes. Yeah. Then what I can do, I can make use of two electrodes.
Hmm.
This is one electrode. This is another electrode. So these electrodes, we call it like cathode and anode.
Hmm.
And they are dipped in a solution.
Hmm.
And that solution can be of any chemical.
Hmm.
Now, what happens is that automatically a chemical reaction takes place
Hmm.
in this arrangement,
Hmm.
wherein at one side oxidation will take place, in another side, in another electrode, reduction will take place,
Hmm.
and a redox reaction will take place. A redox reaction will take place. And what's a redox reaction? A reaction involving both
Hmm.
oxidation and reduction.
Hmm.
It will occur spontaneously, naturally. And because of this redox reaction, flow of charge will be taking place.
Hmm.
This redox reaction, it will lead to the flow of charge. And here the charge is the ions.
Hmm.
Because in the solution, we have ions. So these ions will flow.
Hmm.
And we will be able to derive current through this wire.
Hmm.
If I attach a bulb, it will blow.
Hmm.
If I attach a bulb, it has to blow.
Hmm.
It has to blow. Something. Or we can get some electrode potential. Now, what is the electrode potential? Potential difference between the electrodes.
Hmm.
That is what we will be calculating using the Nernst equation. So now we got an idea what is the meaning of electrode potential, and now we also got a significance of Nernst equation.
Hmm.
Potential difference
Hmm.
between two electrodes. That we will be able to calculate. So this is clear to us. And let us now write the equation itself.
Hmm.
The Nernst equation, let us write that. So the Nernst equation is something like this. E cell, like the electrode potential of the cell, electrochemical cell. It is equal to,
So for the exam, should I draw this figure?
yeah, you can. You
Okay.
can draw this.
Hmm.
Is equals to E naught minus 0.059 upon N
Hmm.
log concentration of product upon concentration of reactant.
Hmm.
Concentration of product upon concentration of,
Reactant.
this is the Nernst equation. So
Hmm.
clearly looking at the Nernst equation, we can see that it is giving us the relationship like how the electrode potential
Hmm.
is related to the concentration.
Hmm.
And this is what is very important, because ultimately what is our goal? Our goal is to derive maximum electrode potential from the cell.
Hmm.
We have to derive the maximum possible electricity from
Hmm.
the electrochemical cell which we have, and Nernst equation will help us to do that. It
Hmm.
will help us to add the right amount of concentration, or take the right amount of concentration in the solution, uh, and because of that we can achieve a very good electrode potential.
Hmm.
Now let us look at the derivation. Now this is the Nernst equation. Let us try to derive this. Derivation of Nernst equation. Like how we got this equation? No? That is the question.
Hmm.
So we know that in an electrochemical cell, redox reaction is taking place. So
Hmm.
let us start with a redox reaction. So I have a redox reaction like this, and I know that in redox reaction, after some time we achieve equilibrium.
Hmm.
In the state of equilibrium, rate of reaction in both the sides will become equal.
Hmm.
Like the concentration of product, like whatever the amount of products are getting created, the same amount of products are getting converted into the reactant. Both
Hmm.
sides the equation is
Same.
operating. So a state of equilibrium will be achieved.
Hmm.
And let us suppose this is a redox reaction, meaning to say that both oxidation and reduction will be taking place in this reaction.
Hmm.
And it's a reversible. Now, one important observation we are making,
Hmm.
because whenever we are doing any derivation, whatever principles we know, we make use of that.
Hmm.
So here, what principle we are making use of is, for a general reversible system,
Hmm.
for a general reversible system,
Hmm.
chemical system. According to Van Hoff's name of the scientist. According
Hmm.
to Van Hoff's isotherm.
Hmm.
See, what is isotherm? Isothermal means constant temperature. If
Hmm.
we keep the temperature of the system constant, we call it isotherm.
Hmm.
And gives free energy.
Hmm.
And gives free energy. According to this, the relationship
Hmm.
or so according to this Van Hoff's isothermal gives free energy, I can write one formula or relationship between the a relation, a very important. Let us write that. So that relation says that delta G, that is the change in Gibbs free energy.
Hmm.
Let me write it bold text. What is delta G? Delta G is minus of RT
Hmm.
log capital K
Hmm.
plus capital RT
Hmm.
log of concentration of product
Hmm.
log of concentration of product upon concentration of reactant.
Hmm.
So this is the relationship between Gibbs free energy and the equilibrium constant.
Hmm.
So the equation I have written, that is basically the relationship between Gibbs free energy and equilibrium constant.
Hmm.
That is the capital K.
Hmm.
Okay. So
Hmm.
this is the idea. Now we will be using this. So this is our first equation.
Hmm.
which we will be using in the derivation. So this is already a established relationship which we are making use of.
Okay.
Okay. Now we also know that we also know that since delta G, that is a Gibbs free energy. Gibbs free energy is equal to like delta G naught. It is equal to minus of RT log T.
Hmm.
So in the main equation one, we can substitute minus RT log K with delta G naught. So this is the second equation. So now what I am doing, substituting 2 in 1.
Hmm.
Substituting equation 2 in 1. Substituting equation 2 in 1. We will get something like this.
Hmm.
We will get something like this that I'm writing. Delta G is equal to delta G naught plus RT log concentration of product upon concentration of reactant.
Hmm.
Concentration of product on concentration and here one very interesting thing which we should know, like what is this delta G naught exactly is, because
Hmm.
delta G to I know delta G is the Gibbs free energy,
Hmm.
but what is this not specifies. So delta G naught is the standard free energy.
Or initial
Yeah.
standard, like before anything happens.
No. So we are calculating the free energy change in the standard conditions. Like
Yeah.
in thermodynamics or in chemistry, there is a STP, standard temperature and pressure.
Hmm.
If we perform any process in a standard condition
Hmm.
and measure the parameters, so we call it the standard. So
Hmm.
standard free energy change.
Okay, so
And that is right. You can call it the initial. So initial here it means Gibbs free energy measured under the standard condition.
hmm.
Standard free energy. This is clear. So now we are getting somewhere.
Hmm.
This is how derivations, the scientists using the phenomena like principles, applying some mathematics,
Hmm.
they get somewhere. And in this way, they derive some magical equations and they become so famous that we are still applying those equations
Hmm. Hmm. Hmm.
and we are studying those equations.
Hmm.
Now see, this I can write like this. Whatever we have got. Now, electrode potential. We call it the EMF, like electrode potential E is equal to E naught
Hmm.
plus RT. So it will be minus RT minus RT log RT by NF log 1 upon MA plus. Here M is the cation, concentration of cation in the solution. Because that concentration of cation in the solution is the one which will lead towards the formation of the electrode potential.
You're
That
talking about the electrode or the one on the solution, sir?
one in the solution. See, these cations, they will always reside in the solution.
Okay.
Yeah, this see in the solution, these cations will reside and they will be attracted towards negative that anode.
Okay, no, I was thinking
Yeah,
like
yeah,
the cathode and anode we are inserting, right, to positive and
yeah,
negative electrodes. They
yeah,
might degrade from the surface of that. Like there is
yeah.
a concept in battery where the
Yeah,
cathode
so
degrade.
when they degrade now, they get converted into ions. Like if let us suppose I am using copper,
Huh.
I am having a copper. If copper is degrading, so Cu2 plus ions is the one which I will be having in the solution.
Okay.
So those ions will be traveling, and those ions are charged, and flow of charge is electricity.
Mm-hmm.
And sometimes we see now, if we dip water, if we dip our hand, we might face like experience current like shock
Yeah.
because it is charged and that charge can flow through our body. And if we are grounded, the charge will flow through us and we can experience a shock.
Yeah.
So I can write it like this: E is equals to, like I am just doing some mathematics. Log, I am reversing it. Whenever log I will reverse it, it will become plus, and it will become RT by NF
Hmm.
log MA plus. Now here we are using some constants.
Hmm.
R is the universal gas constant.
Hmm.
R is the universal gas constant. Its value is 8.314
Hmm.
joule per Kelvin per mole. Joule per Kelvin per mole. Isn't it?
Yes, sir.
Then the next is the standard temperature. Capital T is the standard temperature. That is 298. 298. Okay. And we have F. That is a charge.
Mhm.
Faraday charge. That is 96500 coulombs.
Mhm.
This is the charge. Okay.
Mhm.
So these are the like values, constants we know. Now what we can do, we can simply substitute it
Mhm.
in the equation. And when we do that,
Mhm.
we will get the Nernst equation. Get the Nernst equation. E is equal to E naught
Mhm.
less RT by F. It will become 0.0591. It will become 0.0591 upon N log. This is the final equation.
Mhm. Okay, so we don't need to show like the substituting part and the calculating part and all. Like after that step,
No,
I
no,
can.
no. You have to show everything in the derivation. Like whatever is here, this is the proper derivation.
Done.
Okay. Just
Yeah.